Hello everyone, welcome back to class. Today we are going to be looking at a very lovely question in physics, typically from electric field. And I'm going to be showing you guys today how to solve electric field questions using both algebraic method and the vector approach. Please subscribe to our channel if you know you have not done so. This is the best academy. We are here to guide you in physics, mathematics, and chemistry. Please, when you're in our classes, don't distract yourself by any mix. Ensure you turn on your notification bell so that anytime we release any video, you'll be the first person to see it. Now, let's get to work. The question is, a charge of Q is equal to minus 2.0 microcoulomb is placed at the origin, full stop. Find the electric field at 3 meter, 4 meter, 0 meters. You can also say 3, 4 is still the same thing. Now, recall that electric field is kq over r square. In magnitude, the magnitude of electric field is defined as kq over what? R square. In which you take the magnitude of this q to multiply k divided by the distance between the field and the charge, then you square it. Then in vector form, remember electric field is a vector quantity, so you have to give this a unit vector. Remember, we use unit vectors to denote the direction of a physical quantity or the greater quantity. So if you want to give this formula a vector form now, you use a vector, a unit vector to denote the direction of this, which actually coming from the which is actually coming from the distance or the displacement between this Q and the electric field. That's where the unit vector will be acting or coming from. So I'm going to show what I'm trying to say. Remember, this is the magnitude of the displacement. We just call it distance because it don't have any direction. So called distance. The magnitude of any displacement is equal to distance because it will not be having direction again. When the distance has direction, we call it displacement because displacement is a distance moved in a specific direction. So, but in vector form, we're going to have kq over r square. Then we'll give it the unit vector. Now, this unit vector is the displacement vector over the magnitude of that displacement vector. That's how to express this. The displacement vector over the magnitude of displacement vector. Now, one thing about vector approach is in vector approach, you don't draw. There's no need of drawing. Now, the reason why we draw in electric field is actually to get the direction using electric field lines. Remember, we said electric field lines denote the direction of electric field. That's one of the major reasons why we draw in electric field questions. But in vector approach, this unit vector here will give us the displacement that is actually between this Q and the field. So if you can get the displacement, which is the distance in magnitude and direction, then you're already good to go. You get the direction of the electric field. But if you don't want to use this, you can just draw the question out and use field lines to check for the direction of E. Then you still get the answer in a very good way. So what is the displacement of this vector? The displacement is the point in which this charge is minus the point in which this field is minus the point in which the charge, that is the reference point in which the charge is placed in. Remember, this charge is located at the origin. So, and the self, we should find the field at this point. Now, if you remove origin from this place, you still be the same thing. So that displacement will still be 3, which is to the I direction. That is 3x. That is 3, 4. 3 to the s, 4 to the y. So I'll just call it 3i. Then 4 is still positive, plus 4j. Then if I remove it from the point in which this charge x, which is 0, 0, which is origin, will still be the same thing. If you solve for the magnitude of this, you are going to have the square root of 3 square plus 4 square. You have 5 as your answer. Remember, the displacement are in meters. Then Q is minus 2.0 times 10 to the power minus 6 coulomb. If you move from microcoulomb to coulomb, you are going to have this. Micro means 10 to the power minus 6. Then K is 9 times 10 to the power 9, 90 meters square per coulomb square. Now, let's substitute to see what we're going to have. Now, if you substitute, you are going to have the following. You're going to have your 9, your Q. Now, if you want to place your Q, put the sign with it. If you're using vector, this vector approach, then over arrow square times that displacement vector, which is the displacement vector divided by the magnitude of the displacement vector. That is the unit vector. This one will help us to get the direction of the vector. That's what this one is trying to do here, to get able to get the direction of the vector, which is the point minus the point of the charge. 3,4 minus 0,0 give us this. Then divided by the magnitude of what you are having here as your answer, which is equal to 5. So 5 times 5 square give us 125. Then multiplying this. So if you use this to multiply 3i and divide it by 1, look at how to do it. So multiply this with your calculator, then times 3 divided by 125, you're going to have this I. Then also use this one now to multiply this again, divided by 125, you're going to have this J. What I just mean, open the bracket and divide everything by 125. I and J cannot be added together because they are different unit vector. You cannot add them. It's not possible. Take note of that. So if you look at the magnitude of this, you're going to take the square root of this square plus this one square. So you're going to have 720 Newton per coulomb. This is the magnitude, but this is the magnitude and direction of the vector. So the magnitude and direction now is this, but the magnitude only is this. So please take note of that. It's very, very important. So this is how you use vector approach. Now let's see how to solve this problem with the normal algebraic approach using KQ over arrow square to see what we are going to have. Now using the normal algebraic approach, so you are first of all go to sketch out the vector diagram, the vector diagram of the question. That is, you bring out the charge and the field and the direction of the field. That's what I mean by the vector diagram of the question. Remember, the charge is located on a plane, that is on the Cartesian plane. Anytime you see something like x, y, 3, 4, 5, 6, 0, 10, it means the Cartesian plane in which both s and y will be shown. So s for this question now, they gave us 3, 4. That is 3 to the s. The charge is located at the point 3 to the s axis and 4 to the y axis. So you just measure from the origin. That is, calculate the electric field at the point. Not the charge is located at the origin. You say calculate the electric field at the point of 3, 4. So measure 3 to the s axis, measure 4 to the y axis. Just take a parallel line to the s, take a parallel line to the y. Where they meet, that is the point we're talking about. So this point now is point 3, 4. So look for electric at this point. What is the distance between this point and this point? Using Pythagoras theory, that will give us the distance between them, which is the square of this one, which is hypotenuse, now will be equal to the sum of the square of this other two sides. So arrow square will be equal to 4 square. 3 and 3 are the same thing. 3 square plus 4 square. So arrow will be the square root of 3 square plus 4 square. That will give us 5. Now to get the angle between this line that joins this charge, and I will call this one feed line now. The electric field is going to be moving along this line. So to get the distance between this field and the charge, now what you are going to do, you just also, okay, I've already done that. And they gave us arrow equals to square root of 3 square for 4 square, that is all. But to get the direction between this field and the s axis now, you use the SOHCAHTOA method, which is tan theta is equal to opposite over adjacent. Tan of this angle will be opposite over adjacent. That's what you're going to have. That's what you're going to have. Now, you must know how to sketch out this point before you will be able to get the right direction of this vector. That's just it. We'll be able to sketch out the point where. Then, after I've gotten the angle, I've got the distance. Remember, electric field is KQ over arrow square. KQ over arrow square. Our Q is, remember, we are taking the magnitude only. If you are using this formula, take the magnitude of the field only. Unless you are using the vector approach, in which you multiply with a unit vector. Then, the magnitude of the charge was 2 times 10. The charge was minus 2 times 10 to the power minus 6. But if you take the magnitude, throw away that minus sign. Just take 2 times 10 to the power minus 6 times this divided by 5 square. We're going to have 720 Newton per coulomb. Remember, this was the magnitude of the electric field we got. And it's already depth. So to get the direction now of this electric field, you just check what is the angle between this one and this horizontal. The angle is tan theta is equal to opposite, which is the side facing the angle. This side facing this angle is called opposite. Then this side facing this angle 90, which looks like the longest side, is the hypotenuse. Then this other remaining side is called adjacent. So that your tan theta will be opposite, where is 4/3 adjacent. This side is 3, this side is also 3, this side is 4, this side is also 4. Take note of that. 4/3. Then theta will now be tan inverse of this 4/3, which is this. Then now, if you this other diagram is just coming from here, I'm just drawing this point P, point E here. Look at the point. This point and this point are the same thing. Then I'm just showing this line, and this one. I'm just showing only this, so that you see the actual direction of the field. It's moving to the left hand side of X and to the downside of Y. Actually, check the direction. Check the arrowhead. It's coming downward. That means it's moving towards the left hand side of X. Is going toward the left hand side of S and the downside of Y. Automatically, the field is negative X, negative Y. Remember, in the Cartesian coordinate, negative side of S is S, and the left hand side of S is negative. The downside of Y is what? Negative as well. So let's resolve this one now to the S and Y to see what we are going to have. Let's resolve this field we have gotten. So we are going to have. So if you resolve the field, we are going to have ES equal to, remember I told you it's going to the left hand side. For S, you have minus E cos theta. That is for S, so this one is for X as is. Then plus that of Y. If you want to resolve to the Y as is, now will be minus as well, because it goes to the downside of Y. Then use sine for Y as is, sine theta G. Or you just say ES is equals to, you can just say ES equals to minus E cos theta. EY is equals to minus E sine theta. Yeah, that one is still very, very correct. That one is still very, very correct. You can just say ES equal to minus E cos theta, EY is equals to minus E sine theta. That is if both of them are going, if both of them go to the left and downside. If one goes to the right hand side, the other one go to the down. The one go to the right will be positive. The one go to the downside will be what? Negative. So impute their values. You are going to have this for this. Minus and square plus you have minus. Solve this, you are going to have this. Solve this, you are going to have this. And you can see this was what we are having in the vector approach we did. So this is how you do it using algebraic approach. Thank you.